All right, so good morning. If you logged on, welcome to our second talk in knot theory in this breakout session. So our second speaker is Harrison Gover from the Gatton Academy. He's a junior, and he will talk to us about how much curvature is in a knot.
Hey everybody, thank you all for coming. As he said, my name is Harrison Gover, and I'm going to be presenting my research. But in order to present my research, first we have to discuss how we can describe knots. And that starts with first, what a knot is. A knot is a closed, tangled, one-dimensional figure in 3D space. So to better present this, I'm going to be using a complicated piece of equipment called the iPhone charger. You can take this thing, you can tangle it up, and then you can close it by putting the ends together, and we have a knot. But a true mathematical knot doesn't really have any width like an iPhone charger might. It's theoretically one-dimensional, but it's still tangled in 3D space. But 3D pictures are hard to work with. So instead, we use two-dimensional diagrams. And those diagrams look like these. They are pictures, and they have little over-unders here, which we call crossings. And if you count the number of crossings in a diagram, you can get the crossing number. And if you look at these three diagrams, the two on the bottom have 8 crossings, but the one on the top, I believe, has 11. But what's interesting about this is that they're all the same knot, but these are just different diagrams that represent these knots. So the same knot can have lots of different ways to represent it, and it can have many, many crossing numbers. But the crossing number of the overall knot is the minimum of these diagrams. Next, we move on to the braid diagram. So there are lots of different types of diagrams, and one of them is the braid diagram. And the braid diagram takes a typical knot and puts it around this single dot right there. And it goes in a constant clockwise or counterclockwise direction. And it goes around it. And each braid diagram has this little braid at the top. And the braid at the top is essentially what makes the knot the knot. And the braid index uses the braid diagram and in the way that it's the minimum number of loops. So you can see here that there's this knot turns into a braid, and the braid diagram has 3 loops outside of it, and that makes the braid index 3. We also have spiral diagrams, and those are diagrams that only turn in one direction. So if you are standing on top of the knot and you decided to walk in a specific direction along the knot, you would only really turn in one direction. So you can see on the left knot, it only goes right, and it just goes and goes, and you can follow it with your eyes. And it's the same thing with the right diagram. And using these spiral diagrams, we can get the spiral number. And the spiral number is the number of maxima, the minimum number of maxima in a given knot's spiral diagram. So you can see on the left, there are 3 maxima on the knot. And on these other 2 pictures, I've shown that you can move the knot all you want in terms of rotation of the diagram, but the number of maxima still stays the same. And what's interesting about the spiral number is that it is always less than or equal to the braid index. And this is because it's basically a simplification of the braid index. So you can see here that these are all braid diagrams here. And the braid diagrams each have a center around which the knot travels. But sometimes that's not equal to the braid index. And that's where we get into curly knots. So curly knots have a braid index that is higher than the spiral index. So you can see that in both of these depictions, the knot is constantly moving in a constant direction. However, that doesn't change the fact that it still has a higher braid index, because there's no real dot that you can put anywhere in the diagram that the knot completely travels around consistently. And that's because of these, what we call eye circles in the middle. The eye circles are what cause the braid index to be different in a way. and every single curly diagram has at least one eye circle. There's one other thing, and that is the Fly polynomial. And that is essentially a polynomial that represents the knots and can provide information about them. And the polynomial is essentially a polynomial of two variables, in most cases, A and Z, and it can tell a lot about them. And it's important to remember the powers of A. That'll come in handy a little bit later. So my research is based on a paper that proved that each 3 curly knot can be generalized to this diagram on the left. And the diagram on the left is a knot with 3 boxes, and the boxes are a substitution for a certain number of half twists. And half twists are simply crossings that go, well, they just twist, right? And the more of these crossings that are inside of the box changes the knot. And here's a representation of an example on the right side. You can see that the top box has 1 half twist inside of it, and the bottom 2 each have 2 half twists. And the half twists is the same as the number of crossings. So now we get to the research. So the goals of the research was first to identify more forms of these curly knots. So essentially families of these curly knots and the diagrams that they produce. And we're also looking for trends among these families. But what I believe is the most important goal is to have a simpler method to determine the braid index of a knot, because as it's proven during this research, it can be a bit difficult to find the braid index of a knot. And this can be a hypothetical method to look for it in a better way. So first things first, we can take the diagram that was presented in the paper and expand it to other forms. So what I essentially did was took the 3 boxes and then made it 4, 5, and so on. But we also have to prove that they're curly. And that takes a separate paper by Dr. Klaus Ernst here and a couple others that talks a bit about Montesinos knots. Now, Montesinos knots are another type of knot diagram. It has a top loop and a bottom loop, and then in the middle, it has a series of rational tangles. And rational tangles are essentially just a form of tangle that takes 2 strings and then tangles it up using a specific method. And using that, we can find the braid index. So we can take this form of knot that we've been working with and convert it into a Montesinos knot using a simple transformation. And using that transformation in the transformed knot, we can use these 2 equations on the bottom. Now, I'm not going to bore you all with the details of this equation, but essentially what it does is it takes each individual tangle and it counts its contribution to the braid index, and then it adds it all up and adds 1. And we can do this with this type of knot because it follows a very consistent pattern. So for example, if we were working with 4 boxes instead of 3, it would have 4 boxes in the Montesinos diagram, and 5 would make 5, and so on and so forth. So real quick, do we have any questions? Not hearing any, so I will continue. But of course, there are other types of these knots. The first of which is this interesting one with 2 eye circles and 5 boxes. And the second one is another form of the original knot, but instead of having 1 loop around it, it has 2. So let's work with the one on the left first. And this can have a maximum braid index that is found by a ciphered circle diagram. Now, a ciphered circle diagram essentially takes what Calvin and Ben were talking about, the nullification of crossings, and it creates all these little circles. And these circles don't intersect. They don't form a knot among themselves, but they're representative of the knot. So we can see this knot in the top right, and we can do a simple transformation of that knot. And using the red lines, you can see here that we just added it in. And it's the same knot. it has all of the same properties of this top knot. It's just represented a little bit differently. And using this different representation, we can then get this ciphered circle diagram. And a ciphered circle diagram is interesting because the number of circles in the diagram is equal to the maximum braid index. So you can see here, this diagram has 1, 2, 3, 4, 5, and then one very long ciphered circle. And so that's 6 circles. That makes the maximum braid index 6. So we also need to find the minimum braid index. And this can be found using a proof by induction with the Fly polynomial's A span. So earlier in the presentation, I mentioned that the powers of A would be important. And this is exactly where it's important. Because what we can do here is, first things first, we can create a simplification of this diagram on paper. So we have A, B, C, D, and F, skipping E. And each of these letters represents the number of half twists or the number of crossings inside of this knot here in each of the boxes. So AKA, if it's D11111, that will have 1 crossing in each box. And we can actually find the braid index using the Fly polynomial of a given knot. And that's using the maximum power of A minus the minimum power of A divided by 2 plus 1. And we can find this Fly polynomial fairly easily. You can just plug in the code of the knot into Mathematica and it'll spit out the Fly at you. But we want to do this for all forms of this knot. And that can be found with induction. So there is this equation here that takes the Fly of the positive crossing knot. You can take one crossing and make it into what we call a negative crossing. And we can also nullify that crossing as Ben Calvin explained. And we can use these two Fly polynomials to produce another Fly polynomial. And this essentially works in induction because if you have 2 given knots, you can essentially continue the list and make more and more knots upon that expansion. And by expanding that, we can create a general form, and that makes the minimum braid index also 6. And what this means combined with the maximum braid index of 6 is that we can guarantee that knots of this form have a guaranteed braid index of 6. Next slide there. This is not responsive. Oh, here it is. Okay. So now we're going to go on a short tangent, and that is alternation. So in each crossing, there is an over and there is an under. So one strand goes over and one strand goes under. When I say that a knot is alternating, I mean to say that if you were to walk along the line of the knot, it will go over, then under, then over, then under, and so on and so forth. And we can prove that every knot of each of these forms must be alternating. So I have an example of a knot that we have is curly, and it has 2 portions of the knot. The first is this central circle here with 4 crossings. And the second is the outside with the boxes. So first we can prove that the central in this little cutout here, you can pull one of the strands over and it completely gets rid of the central eye circle and it completely changes the knot and it makes it non-curly. We can also see that the outside has to be alternating as well, because if it's not, such as in this example, we can take the top and the bottom in this segment right here and pull it out so that it creates an alternating knot. And finally, the crossings on the outside have to be alternating to the crossings on the inside based on this diagram here, which shows that if it is not alternating, then you can pull it aside and make it alternate. So because of these three ideas that this has to be alternating, this outside has to be alternating. So short tangent here, another one. Here we go. So knot theory has a lot of computer science, as Calvin and Ben have explained. And this is what you're looking at right now is a file produced by a friend named Matthew Pimienta, who used to be part of the knot theory group. And he has produced a Python code that creates this specific type of knot with the 5 boxes. And it's a very long even moving. And it shows that when studying knot theory, there's quite a bit of code. And it's actually very useful because these PD codes that are produced each represent a knot. And it's what better allows for a type of knot to be studied in Mathematica. So let me go back to the presentation. Give it a second to load. Not sure if it's showing on you guys' screen. Okay.
Not there yet. I'll let you know when it's there. Okay, now you're there. Not there yet. You know when it's there.
Now I can see it. So what's the future of this research? First, we need to prove that this double loop knot is curly because we're just finishing up with the induction. The next step is to figure out this family. And a bigger future behind it is to find more general trends among curly knots. So for each type of diagram that we produce, we can prove in some manner that it is curly. But an interesting concept to continue this is the idea that we can have some kind of big equation that represents with a number of boxes or a number of eye circles that can end up proving whether or not any given knot is curly. And this is an interesting concept. I definitely think it's a good future for this kind of research. So that's a bit of an early ending, but that is the presentation. Any questions?
Any questions for Harrison? Harrison, can you go back and show us a picture of this family you were talking about? Why are these things curly? I don't think that for people who are not used to it. Can you go back and show us a picture of this family you were talking about? Why are these things curly?
This knot?
No, the one before where you actually can prove that. I mean, about this one, we haven't proved anything. Like, for example, the one where you talked about the home fly polynomial calculation. This one, your slide 17. Polynomial calculation. This one, your slide 17.
We're trying to click on it, it's not exactly responding.
Sound is bad. There's some sound is bad. There's some. Yeah, tell us why this is curly.
So can you guys hear me?
Yes. Yes. Harrison, what's the number of maxima you see there?
I think he's frozen.
Yep, he may have crashed. I mean, sound got kind of bad for him.
Harrison, you might try turning your video off to see if that helps your internet. If you can still hear us.
Yeah, probably. You probably can't.
Yeah, he's frozen.
Okay. Let's be patient. I think Harrison may log back in and see what if he comes back. Harrison, can you hear us? Well, that's a bummer. Look, Harrison, are you back? Well, let me just say that much. With the work Harrison has done up to this point, I have been very impressed. Because this is a non-trivial thing he has picked up, and he actually has produced some results which are quite impressive. Harrison, can you hear us now? Ah, he's back.
Yes, my Wi-Fi crashed for some reason.
Yeah, go to slide 17 and explain to us why such a thing is curly, for example. What makes it curly? Into us why such a thing is curly, for example. What makes it curly?
So what makes it curly is the fact that we can prove that the braid index is 6. And since this right here is a 4 spiral knot, and it has a braid index of 6, that means that the braid index is higher than the spiral index, which therefore makes it curly.
Thank you. Anybody else? Any questions for Harrison? Well, then let's thank our speaker. You can either do this by clapping, or you can sort of blend in your virtual reaction of clapping hands, whatever you want to do. But thank you, Harrison. And thank you all for coming. There are going to be, again, a team of 2 to talk. One of them is Nathan Gilsby, who is a Gatton senior. And this knot theory in virtual reality was an idea he cooked up to do a summer rig last summer with me. And you all know what happened to those. They got canceled because of COVID, which was sort of really unfortunate. Nevertheless, we did some Zoom knot theory sessions over the summer. And he got actually the Gatton Academy to come up with some funding. And so he actually has one of those Oculus devices. And the other person is DJ, or Donald Price, who is a graduate student, and he has gotten also an undergraduate degree from WKU, a former Gatton student. So he has been around for a while, and he is really, really good in writing programs in all sorts of languages. His skills have by now far surpassed mine, even so he was a student of mine in CPS when I could have claimed that I can still do better than him, but that has certainly switched. And these 2 guys have teamed up to talk about knot theory in virtual reality. So hereby I turn it over to you. It's approximately 11:15-ish, and so feel free to get started.
PJ.
Sure. Yeah, I'll introduce this. So we'll be switching back and forth throughout this talk. And so like Klaus said, I'm DJ. And so this project is supervised by him. This is partially in towards the completion of my my graduate thesis. And so there's a lot of things, that we split up between the work between me and Nathan. A lot of different sorts of things we work on. Today, what we'll mostly be showing you is kind of the flashy things about it, or the cool to see things. So if you go ahead, Nathan. So we'll give you a few definitions. If you've been here at all this morning, you're kind of chock full of definitions at this point. But for those who have joined since the beginning of this talk, we'll still give a few of them. It's good for you to know. We'll tell you about the motivation, why we're doing this. Building a virtual reality project isn't a trivial thing to do. So we want to justify, why this is a good thing to do, and why this is interesting. We'll demo some stuff we've done. So we've officially started this project as of about January, when the semester started, with a little bit of work done before then. But we'll demo what we've got so far, and then we'll talk about some goals that we have that we're going to complete by the end of the summer, basically. And so with that, I'll turn it over to Nathan to start telling you some example or some definitions.
Yeah. So first, let's start by defining a knot. In our case, knots are kind of inspired by the knots that you see on the left, real world knots. But these aren't knots. Knots are closed, non-self intersecting curves. So they're really one-dimensional. But to help us visualize them, we create this tube version. So kind of this image that you see on the left is typically how we'll represent knots. And this is in 3 dimensions. And with that, whenever we look at knots, typically we look at them on screens, like on paper or some 2-dimensional surface. So that requires us to make a projection. That requires us to take all the points of a knot and then project it onto a flat page, as you see down here. And what this image down here at the bottom is what we call the diagram. Now, diagrams have crossings. So you can see indicated by this point here, here, and here. And it's good to quantify knots using those crossings. So we make knot tables. In this case, 0, 1, 3, 1. This first number here is the number of crossings. So you can see 3, 1, or the trefoil. No matter what way you manipulate this knot here without passing strands through itself or passing the curve through itself, you're always going to end up with a representation that looks like this or a little bit more complicated than this. So since this is the first one of its kind, we call this 3-1. And then we do this for all the knots. So so far we have tables up to maybe 15 crossings. Yeah.
So what has motivated us to do this project? Of course, this was Nathan's idea in the first place, because he has had some experience with other virtual reality applications, and I believe he presented at the last math symposium when we were still seeing each other's faces in person, a really cool virtual reality application. And so why is it useful? Why is it useful to have software for this in the first place? We can certainly draw knots a lot, but it's extremely useful to have computers interpret the knots. And we can represent knots in computers with different sorts of methods that we don't define here because it's not entirely too important in this talk, but there's ways to represent them with numbers and ways that computers can interact with them, move them around, and do things with them. And we can apply different algorithms we come up with through them. The 2 most prevalent pieces of software that we've been experienced with, one of them is Knotplot, which is a very sort of general purpose sort of tool. It's got a lot of different things in it that you can do. You can look at different knots. You can see kind of 3D images of them. You can do different physics simulations on them. And I believe Nathan can play that video in the slide.
But yeah.
Possibly. Cool. And so this is an example of knot plot, and what it's doing is it has this really complicated knot that's tangled up and has a bunch of, you know, unnecessary crossings and windings and so on. And it's applying basically a physics simulation to it. So this is one thing that exists, and one thing that's really cool, because we can see this simplifying the knot. One thing that's interesting in knot theory is to look at something and say, is that the simplest version it could be in? Can it be simpler? How can you simplify it if it's not as simple as it can be? And doing this sort of physical manipulation on it and minimizing, getting rid of all these tangles, is one way that we can analyze knots. And so it'll keep running, and eventually it'll get down to a 7 crossing knot. And then on the left, you see the bottom left of this slide, you see a drawing. And so we mentioned briefly what a projection of a knot was. Basically, if you shine a light on a knot, you can see it in 2D on a plane. And the knot theory package in Mathematica that we use a lot, so basically everyone that's presented this morning uses that package a lot. And that allows us to draw projections of knots. It allows us to manipulate different properties of the knots, calculate invariance of a knot, things like that. So these things are really useful. Go to the next slide. But none of these applications use virtual reality. VR, we believe, will make research easier. It's much more conducive to research if you can see the 3D object that you're trying to manipulate and look at. There can be some things lost when trying to draw diagrams, or at the very least, it's a little bit more difficult to conceptualize what's happening when you see the diagram. It will make it easier to get more people into the research, make it a little bit more accessible, make it more interesting, and of course it'll make it more exciting. If you can see a knot in front of you, you can, you know, draw a knot or look at a knot that's been made before, or even if we can see that sort of physics simulation you just saw in virtual reality, that will be really cool. So you can actually walk around the knot and watch it as it's simplifying or doing something like that. So you can go ahead.
So what we have now is a few demos of what we currently have. Right now, this is just an animation of the treble that you saw before, but now it's inside a scene in Unity. Unity is kind of the thing that we use to make all of our application. But what I'm doing here is I'm changing the radius of this tube, which goes around the knot. And of course, keep in mind the tube isn't actually there. It's just it's to help visualize. But this is to show that we start with a set of 3D coordinates, or an ordered list of 3D coordinates, and that defines our knot. And then from there, we take and fill around with basically a tube. So that's an example of that. Also, as DJ said earlier, we use virtual reality. This is the headset that I use. It's like the Oculus Quest. The most important part, though, is it's basically with a computer, so it can run on its own. And it has 2 eye things here, and that's to simulate 3 dimensions. So that's to kind of like trick your eyes into thinking that you're seeing 2 things in 3D when you're really not. So what I have in this video here is just the left eye. So although you can kind of see like me in the bottom right corner here, moving my hands, I'm using, oh, and by the way, I'm using hand tracking technology. So this thing also has cameras on it, which can help, you know, track the positions of your hands and track the positions of various parts of your hands, like say your fingertip or the pad of your finger and so on. So you can calculate the distance between different parts of your fingers. What I did here was I just kind of pinched my fingers to draw knots, and then our program can detect pinches, and we can draw knots that way. So here's kind of an example of that. So I think I tried to draw 4-1 here. Kind of worked. kind of deleted that one accidentally. But I'm also using this kind of gesture to delete knots. I think we could do a lot more gesture detection, but this is what we have so far. It also allows for drawing of links, although we didn't really mention this before. Links are essentially like knots, but with multiple components. So if you imagine taking two knots and then kind of putting them together so that they still don't intersect, we call that a link. So that's kind of what this is.
So if you could release the screen share there for a sec, Nathan. I'll show you all just a little bit more. I want to mention this as well. Nathan mentioned that we're using Unity, and essentially what Unity is, it's a game engine is what it is, but we're using it to interact with these VR headsets. So what I want to show you is that you can still use this. We have some functionality that will be available without a VR headset, and so part of that is because I don't have a VR headset. We've applied for some funding to try to get me one, but they're quite expensive. So there are some things you can do without the headset, and this isn't in the scope of the project right now, but after the completion of this thesis, we'd like to put a lot of focus into making this to where you don't have to have the headset, but that it's a really nice thing to have, because well, we don't want to add that to the scope of the project now, because anyone that's done any software development knows that the first thing to kill a project is by adding a bunch of requirements to it. So we're trying to stay focused and keep going in one direction. But we can look at different knots here. So Nathan showed you the knot table earlier. So we had 3 sub 1, so the 3 crossing knot when you project this, the first in the table. So we have one crossing here, another crossing here, another one here. If we were to project that onto a plane, I can move up to the first 4 crossing knot. And that looks really cool too. I can rotate this around a little bit, look at this in different ways. Look at the first 5 crossing knot, the first 6 crossing, the second 6 crossing. And so we just have a few of these preloaded into the program right now. These are sort of the most common, like, canonical knots to look at. The other thing we've done is you can look at links. So Nathan mentioned that briefly as well. We can draw, more than one of these figures. I believe the next one is the 4 crossing link. We have some 6 crossing links that look pretty cool too. Look at them from weird angles. And then we can even look at something that has more than 2 components. So the number of components here doesn't matter. So we've got one separate thing over here, one separate thing over here, one separate thing over here. And so to kind of conclude this talk,